All right, so maybe from your rule of 13 and a mass spec, you think that your formula is C6H12, right? And so it's C6H12. There's a bunch of different compounds that you can draw that are C6H12, right? A bunch of different constitutional isomers. For example, you could draw cyclohexane. You could draw cyclohexene, where the double bond can be in any one of these places. You can draw a cyclopropane with a methyl, or you can draw a cyclobutyl with two methyls. However, if you try to draw just regular hexane, while that has 6 carbons, it does not have 12 oxygens. This formula would actually be C6H14, right? So how was I able to quickly draw these compounds and identify that this was not an option? And that was using this degrees of unsaturation, which we can find from our molecular formula. And the root of this kind of little trick comes from the fact that our chained or branched alkanes always have a set number of hydrogens related to the number of carbons. And so if you have a straight chain or branched alkane, you always have a certain number of carbons, and then the number of hydrogens will be equal to twice those number of carbons plus 2. Right? So for example, if we think about hexane, right, we see that we have 6 H's because it's hexane, and then each one of these carbons has at least 2 hydrogens on it. And so that's where the 2N comes from. So in this case, it's 2 times 6. Just forgot about these two. And then also at the end points of these carbons, there's going to be an extra 2 hydrogens because we don't have carbon-carbon bonds here. And so that's where this plus 2 comes from. And so this is C6H14. And branching doesn't matter, right? If you think about a branched molecule like that, if it's still got 6 carbons, it will still have 14 hydrogens. You can do a couple examples yourself to prove that this is true. And so what we say is that all of these compounds are saturated with hydrogens, right? They've got the maximum amount of hydrogens that they can have. And so when we have something like our scenario up here where we have C6H12, right, we're missing 2 hydrogens. And so the rule goes for every 2 missing hydrogens, you have 1 degree of unsaturation. This is also sometimes called the hydrogen deficiency index, which gets abbreviated HDI. I like degrees of unsaturation. That's always the way I've been taught about it. But if you want to use HDI, that's totally fine too. And so a degree of unsaturation is something that removes 2 hydrogens. And so this can either be a pi bond. Think about if you have an alkene versus an alkane, we eliminate out 2 hydrogens. Or rings, right? Any sort of cyclic structure will also eliminate out 2 hydrogens. So for example, if we have C6H10, if we think about it, what our rule should be, it should be C6, and then 2 times 6 is 12, plus 2 is 14. And so what we're missing is missing 2 pairs of hydrogen, so there's 2 degrees of unsaturation. And so we can think about what those things can be. Obviously, we need to have 6 carbons, and then we need to have 2 degrees of unsaturation, right? So maybe we have something like an alkyne that has 2 pi bonds and thus 2 degrees of unsaturation. Maybe we have something that has 2 alkenes, which each pi bond is a degree of unsaturation, so we have to have 2 of them. Or maybe we can mix it up. We can have a ring, and a pi bond, right? The ring is 1 degree of unsaturation. The pi bond is the 2nd degree of unsaturation. Or maybe we can have something that has 2 rings, right? This last one probably pretty unlikely, but nonetheless, it has 2 rings, so 2 degrees of unsaturation, right? So what you can do is use your rule of 13 to get down to a plausible formula. From this plausible formula, you can draw different constitutional isomers that may or may not be your compound.